Hello class, welcome to another lecture. I'll have to pull up on my website, see which lecture number we're on now. So I'm on the computer. This is lecture number 6. We'll call this Intro to Sequential Systems. So I'm trying something new with the video. I've turned my paper into landscape view, and hopefully this will work out better. It'll be a little bit more awkward for me to write the notes because I'm coming from just regularly written up and down. And I know with the Acrobat viewer you can turn these 90 degrees. So I'm going to kind of meld everything from Chapter 6 and Chapter 7 together. Chapter 6 is analysis. Of sequential systems, and Chapter 7 is design of sequential systems. So remember, we talked briefly about a sequential system at the beginning of the semester. Sequential system, or you can call it a finite state machine. The output depends on present input and past history. So this type of system will have a memory. These are clocked systems. Sequential systems that we're going to look at are clocked systems. I'm not aware of any others that exist, although I'm sure there are. But we'll see, as we've talked about, a clock alternates. B/T is between 0 and 1 at a regular rate. If you look at figure 6.2 in the book, it looks kind of like this. These are the outputs to the system. Here's our inputs, x1 through x sub n. In the middle here we have memory. Q1 through Qm. And we have some signals here. So everything inside this kind of big wide U shape is combinational logic. We've talked about that all semester. It's not going away. What we'll be focusing on is this part here. How do we program the memory to keep track of what we need it to keep track of? Memory will store bits representing a state. And we'll see an example of that in a moment. First, there's one other topic that I want to go over here. And this is especially important for engineers, computer engineers, electrical engineers, and a couple of definitions. Period. And we represent it with the symbol T. It's measured in time, so maybe seconds, milliseconds, microseconds, nanoseconds. It's the length of one cycle. Another way to say that is that it's the time between two consecutive rising edges or two consecutive falling edges. Frequency is 1 over t, 1 over the period. It's cycles per second. And it's measured in hertz. And so we'll have an example of this now. So let's say that the frequency equals 200 megahertz. So that's 200 times 10 to the 6, mega for the 10 to the 6. Two different ways to express that same number. And then we can say, what is t, the period? Well, we were just given a very simple formula. 1 over t is equal to frequency. Flip both sides, and this gives you t is equal to 1 over 200 times 10 to the 6th. And t is equal to 5 times 10 to the -9th seconds, which is equal to 5 nanoseconds. I should have said that this is hertz up here. Got rid of the mega. So that m, megahertz, refers to 10 to the 6th. So nano is 10 to the -9th. So here's time on this axis. So what we've just calculated is right here. Excuse me, that's a typo. And that's drawn very poorly. Time between two rising edges, or the time between two falling edges. This is rising, it's going from 0 to 1. This is going from 0 to 1. Or right here, two falling edges. To visualize the period, we can't draw that many of them. There's 200 times 10 to the 6th of these in one second. extremely fast. Although by CPU speed, that's really not all that fast. Right, so like I said, extremely important for engineering disciplines and good for computer science to understand that as well. And that's from the book. And we will look at some more timing diagrams like that. There's one in the homework. All right, page 3. We saw this example earlier in the semester and said we'd defer it till later. Output Z is equal to 1 if and only if input X has been 1 for at least 3 clock cycles. So time and memory are now elements in our circuits. And we're not going to build any actual circuits today. We're just kind of wrapping our head around what's going on. We have to understand what's going on before we can actually build a circuit out of it. So this is a timing trace for the example above. And we're given a series of inputs, and we'll have to come up with the outputs and the states. And there's no state in this example. So this is a homework quiz and a final exam topic. So X has the following values: 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 0, 1, 0. So ask yourself, what's Z right here? What's the output at the beginning? We don't know, because we're just coming into the system at this moment in time. We don't know what came before this. So we don't know if there's been 3 1s yet or not. So we're right there. We don't know initially what we are. There could have been 3 1s. There could have been a 1, 1, 0. It could have been anything. So we can't know right there. What's not in the book is these arrows I'm going to show you. This 0 tells you what comes next. I should go up here and add the word consecutive, 3 consecutive clock cycles. So if we have a 0 here, the output's going to be 0. Even if there were 3 1s here, this 0 broke the chain. Now this 1 drives this next output. It's only a single 1, so the output's still 0. Remember, we're counting up to 3 in a row. Here's our second one in a row, so our output's still 0. And then this one broke the chain again. So we stay at 0, and we reset our count to 0. Now we've had 1, we've had 2, and now this 1 is the third one in a row, so now it drives the next output to be a 1. So an important point here, I'm going to take this from the book. the output depends only on the present state, not the present input. Therefore, output occurs after desired input pattern. So what this means, and this is directly from the book, I added a word or two for clarity. This 1 happened after we got 3 1s. And you'll see this come out a little bit more clearly when we actually define a state table for this system. This is known as a Moore model. And the Moore model, the output depends only on the present state, not the present input. And I'll show you other ways to recognize the Moore model going forward. You'll need to know the difference between a Moore model and the other one's a Mealy model, which we'll talk about in a moment. So this 0 resets our counter. This 0 resets our counter. Here we've received 1, received 2, received 3. Excuse me, that should be a 1 there. That's our third 1, so that drives that to be a 1. That's a 1. That brings it to a 0, brings it to a 0. What about here? Put a star there. Continue output as far as possible, even after known input stops. This is a 0, so we know this is going to be a 0. If it's zeros all the way, or just 0, 1, 0, 0, 1, 0, 1, 1, 0, we know it's going to be zeros. Look at the case where we had the output change. We had a 0. We can kind of compare this spot to this spot. Even if we got 3 1s in a row here at these unknown inputs, we'd still have 3 more zeros. And now right here, I can't be sure. If these are 3 1s, then that's going to become a 1. If this has any zeros in it, this would still be a 0. But at this point, we don't know. But we know we'll get at least 3 more zeros here. There's no hard and fast rule about that. You have to reason through it. And we'll look at several examples where I will continue the output until you can't tell anymore. So the output will either be a function of current state only, which is what we just looked at, which is a Moore model, or B, function of current state and current input, and that's known as a Mealy model. So, there you have it. There's our first timing trace. And we will use a state to represent how many ones we've received. Should be EI, I believe. So in this case, the state of the system is how many ones have we got in a row? It's stored as binary in memory. The memory device is called a flip-flop because it flips and flops between zeros and ones, depending on the input signals that you give it. We'll learn how to store ones and zeros in memory. We're not getting to that today, like I said. Memory is a binary storage device. Each FF for flip-flop stores a bit, 0 or 1. So we have to encode and define the states. This is a design decision. It's up to you. I'm going to pick, well, first of all, how many states do we have? We've got the state that's a state. We've received 0 ones. This is receive, RCV. We've received 1 1. Received 2 ones. And then we've received 3 or more ones. So the output will be 0 in this case, 0 in this case, 0 in this case, and then once we receive 3 or more ones in a row, we receive a 1. So I'll call this A, B, C, D. We've got 4 states. How many bits do we need? 2. So we can call this 0, 0, 0, 1, 1, 0, 1, 1. I could have gone 1, 1, 1, 0, 0, 1, 0, 0. I could have mixed these all up any way I want to. I just have to be consistent about it. Once I've decided this order, I've got to stick with it. So Q represents our current state, Q star represents the next state, and so in this case, I've got 2 Qs because I've got 2 bits, so Q1 and Q0. So these are just separate 1-bit variables. I'm using subscripts to differentiate between them. So here's our state table. Present state, A, B, C, and D. Next state, we need a column for x equals 0 and x equals 1. You can also put x equals 0 over here and x equals 1 over here, and it doubles the length of your table. Here I'm splitting the next state into 2 different columns, and we'll see examples of that as well. Let's jump to the output line because that's the easiest one, and we've already done that up here. In state A, we were output of 0. Try to keep things somewhat lined up. In B, it's a 0. In C, we receive 2 1s. And in D, we receive 3 or more 1s in a row. So if we're in state A and the input's a 0, it's going to take us back to state A. If we're in state A and we receive a 1, that transitions us to state B to count that 1 1. So in memory, we will store, if our input is a 1, we jump from 0 0 to 0 1. Remember, this is stored in a binary storage device. Don't get too hung up on that. I want to point it out now, but like I said, we'll get into the actual design of the circuits in the next lecture or two. If we're in B and we receive a 0, we go back to A because that resets our counter. If we receive a 1 over here in this column, that means that we go to C to count 2 1s. That's what C means. In state C, if we receive a 0, we reset our counter, go back to A. If we receive a 1, we go to D. But again, while we're in C, we're still outputting a 0. Now in state D, if we get a 0, that takes us back to A. If we get a 1, we stay in D. And that is our state table for this particular problem. We can tell it's a Moore model from this because the output doesn't depend on the input. Only depends on the state. Alright, I wish I had room on this page to put up the state graph. I don't. You may want to keep this page handy. And I'm going to go now to the state graph or state diagram. So this is what each bubble represents. We have the state and the output. For the Moore model, output goes inside the state bubble. Because in state A, we have a 0. Now go back to your state table that we just built. If we have a 0, we stay in state A. If we get a 1, we go to state B. And the output in state B is 0. From B, if we get a 0, we go back to A. If we get a 1, we go to C. Output in state C is 0. If we get a 1 from C, we go to D. And there the output is 1. So you can see we've gotten 1, 2, 3 1s now. From C, if we get a 0, we go back to A. From D, if we get a 1, we stay here. And from D, if we get a 0, we go back to A. So these two things that we've looked at, the state table and the state diagram or state graph, are crucial to designing your systems. Once you put these together, really not much else changes. This is really the only super new stuff. Because from this point, we take the state table. Now, our current state table we need to get a little bit more detailed with it. We need to be completely binary. But then we can turn it into K-maps. And so this is, like I said, this is the design process. And then we use techniques that we've already learned. I'm oversimplifying saying this is the only new stuff. There are some other new things, but a lot of overlap with what we've done. state diagram has same info as the state table. Let's do timing trace again. And this is the one (6.2), page 369. I'm just going to start it for you. So X, we have 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1. And we have 5 of those in a row. 2, 3, 4, 5. And then 2 more zeros. This is our state. This is our output. So we've added state now. Sometimes you're given the starting state. This time we're not. We don't know what the state is that we started in here. That's a question mark. And so we don't know what the output is because we don't know what state we're in. It's the same as the last timing trace we looked at. Anytime we receive a 0, we go to state A. Look at the diagram up here. Look at your state table. It's either one that you want to look at. They both have the same data. One, this is more graphical, visual. The other one's a table. You'd look it up. And by look it up, look here. Anytime we have a 0, we always go back to state A. And then this A tells us what our output is. Output 0. Now both the 1 and the A inform us where to go next. If we're in A and we receive a 1, we go to B. And then this B tells us that the output is 0. B's output is 0. So there again, a 1 and a B takes us to state C. State C, the output is 0. C with a 0 takes us back to A. State A, the output is 0. I'm just putting in the arrows to kind of show you what values here tell you what to fill in. You don't have to write the arrows, and if you look at the example in the book, the arrows aren't there. A with a 1 goes to B, output is 0. B with a 1 takes us to C, output is 0. C with a 1 takes us to D, output is 1. D and 0 goes to state A. A with a 0 stays in A. A with a 1 takes us to B. B with a 0 takes us to A. Creeping up here. A with a 1 goes to B. And you could also just do all the states and then do all the outputs if you wanted to. Sometimes I do it like that. So from here on out, I'll just do the states. B with a 1 takes me to C. C with a 1 takes me to D. D with a 1 takes me to D. D with a 1 takes me to D. D with a 0 takes me to A. Then we'll talk about this. B is 0, C is 0, D is 1, D is 1, D is 1, A is 0. So you need to know how to do this for quizzes and tests and the homework. So practice this. Start off with just X. Where I started this problem, I gave you the whole X row. That's your input. And then you have to fill in Q's and Z's all the way down. We're going to continue now. How far can we go? Well, A with a 0 obviously takes us to A, and the output will be 0. We don't know what the input is moving on here. If we get any zeros before we get 3 1s, we're just going to keep moving back to A and keep it zeros. The only way this is going to change is if we get 1 1, 2 1s, 3 1s. So we could potentially go to B here with a 0. We don't know what the state is, and then we could go to C with a 0. Or we could stay in A in both cases, but in either case the output will be 0. And then here we don't know what the output is. Because we could go A, B, C, D. We could go A, B, A. If we go A, B, C, D, this becomes a 1. If we get any zeros in this bunch up here, then this would stay a 0. So here's the first time we don't know, but we know these are all going to be zeros. But again, we don't know the states. We could go to A again if we got a 0 here. If we got a 1, we'd go to B. If we got a 1 again, we'd go to C. We'd still have a 0 here. If we got a 0 here, then we'd go back to A. But if we got a 1, we'd go to D. So make sure you can reason through that. All right. Same problem, but we're going to look at this from a Mealy model standpoint, and this will be the last topic for this lecture. Just take off my sweatshirt, get a little bit warmer here. And here comes my dog saying hello. You hear her tail flapping. Go sit down. All right, so A will be no 1s, B will be 1 1, C will be 2 or more 1s. We don't need a D. Why? Because if we're in state C and the current input is 1, that's our third 1. And that'll give us an output of 1. It's a little bit kind of subtle, but let's look at the state table. So if we're in state A and we receive a 0, we stay in A. If we're in B and we receive a 0, we go back to A. If we're in C and we receive a 0, we go back to A. Remember, this is the current state, next state. Current state, next state. If we're in A and we receive a 1, we go to B. If we're in B and we receive a 1, we go to C. If we're in C and we receive a 1, we stay in C. Notice here, this is different. Go back in your notes, look at the previous 2 pages ago. I'll pull it up here. Output only depends on the state. There's no x equals 0 or x equals 1 here. That's a Moore model. This is a Mealy model, what we're looking at now. Output depends on the input and the state. So in either case here, in state A, we'll output a 0. In state B, we output a 0 in either case. If we're in state C, we've gotten 2 1s, but if then we get a 0, our output's a 0. If we get a 1 in state C, here's where we finally output a 1. State diagram. So for Mealy, output is associated with transition. So again, note the difference. You'll have to be able to do both kinds. So state A, we don't put the output here, put it here. And for a little kind of legend of what this is X over Z. Input 0, output Z, output 0, we stay in state A. Excuse me. B. A 1 takes us to B, we output 0. A 0 from B takes us back to A, and we output a 0. If we get a 1 from B, we still output a 0, go to state C. If we're in state C and we get a 1, we output a 1. If we get a 0, we go back to A and output a 0. So now we're going to look at trace 6.3 on page 370. And this is the last topic here. There's a typo in your book as well, and I'll point that out to you. Here comes my dog looking for some petting again. Maybe I'll put her in a video one of these days. All right. So looking at page 370, right here, under this C, look, we're in state C. The current input is a 1. This output should be a 1. So X, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, and then 5 1s, and then 0, 0. So there's your problem setup. Now then, we're not given the start state. You'll be told if it starts in a specific state. If you're not told, then you just have to use a question mark there. Anytime, if you look back at our state graph, pull that up, anytime the input is 0, the output is 0. That's this column here. So it doesn't matter which state we're in, we do know the output here because of this input. So anytime the input is 0, that takes our state to A. A with a 1 is going to be an output of 0. So both values drive that, and both values drive us over here to the next state, which is B. Both values here give us a 0. This takes us to say C, but the input is now a 0. So that keeps our output as 0, as it should be. This takes us to state A. This takes us to state B. Output of 0. This takes us to C. C at a 1 gives us a 1. So all I'm doing is tracing this information here. So let's go back to right here. I'm in state A. My input is a 1. I go to state B right there, and my output is 0 right here. State B, my input is 1. I go to state C. B, my input is 1. I output a 0. State C, my input is 0. I go to state A. Input is 0 here. Go to A. And I output a 0. So jumping ahead, here's C. Input is a 1, so I'm going to stay in state C. But now here, I go to 0 because of this. And the rest of it's in the book, so I'm not going to go through the rest of it. That's how you fill this out. You should practice it. All the material I covered today was 6.1. I'll write that back in at the beginning. I wish I could put it at the beginning of the video. I probably should have said that. But there it is. All right. Y'all stay safe out there, and I'll see you again soon.